Okay, welcome again to Let's Talk Chemistry with Pastor Dan. We've been talking about gas laws. We looked at the combined gas law was a combination of Boyle's law, constant temperature, P1V1, P2V2, where they're inversely proportional, pressure goes up, temperature goes down. Charles' law, where we're talking about constant pressure, V1 over T1, V2 over T2, they're directly proportional. And then Gay-Lussac's law at constant volume, P1 over T1 is P2 over T. Put them all together, we get the combined gas law, P1 V1 over T1, P2 V2 over T2. Today we're looking at two gas laws. We're looking at Dalton's law first. Dalton's law says the total pressure in a closed system is equal to the sum of the partials. Now, what do we mean by closed system? We need to keep everything inside so we're not missing anything. And you might remember this, Dalton. This is the same John Dalton, who's the father of atomic theory. So we're saying that one individual gas added up inside of a system, we add them all together, we get the total pressure. Now, there's two different ways that we can do, three different actually. If we know the individual pressures, just sum them up, we can find the total pressure. But we can also go the opposite way. If I know the total pressure and I know the individual gases, I can find the partial pressure. Let me show you. So let's say I look at a problem like the following. Calculate the partial pressure of 12.350 liters of chlorine, 14.220 liters of oxygen, and 13.430 liters of nitrogen in a vessel with a total pressure is 112.98 kilopascals. So what we're going to do here, to find the pressure of our individual gas, gas A, whatever it is, we're going to take the volume of that gas as opposed to the total volume. What we're actually doing is finding the percent, what decimal percent is that gas inside that container. We then multiply that by the total pressure and we'll find the partial pressures. So we take our three gases here, chlorine, oxygen, and nitrogen from the problem, and we're going to add them up and we get 40.000 liters, sig figs, last failed column. So put our values in for chlorine. We're going to take our volume of chlorine, divide by total volume. That decimal times the total pressure will give us the partial pressure. So we're going to take 12.350, the value we have for chlorine, divide by 40, the volume we have for the total volume, multiply the total pressure, and sig figs 5, 5, and 5. Using our calculator, take 12.350, divide by 40.000, hit equal, multiply by 112.98, and we're going to get 34.883 kilopascals. Now I'm asking for all three here. So let's do the next one. For the next one, we're going to take 14.220 liters, divide by that 40 value times low pressure, and we're going to get our 40.164 kilopascals. And then although the answer is there, we also do the same for nitrogen, which is going to be 13.430 divided by 40. Now, those are our answers. There is a check here, though. If I'm asking you to find all of them, if you add them all up, you should get the total pressure that you started with. So that's one of the ways we can do it. Second way we can do it is in a scenario like this. Determine the pressure of carbon dioxide collected over water. When we collect gases, we often collect it over water. We need to know the barometric pressure. And it's very efficient for these problems to keep it in millimeters of mercury. Where they used to do it, they used to take a bowl of mercury and a capillary tube. We don't do that anymore because mercury is not good for us. So here's what we're going to say. The total pressure is equal to only two gases. We have carbon dioxide, and what's the other gas there? Well, remember, we're collecting over water. Some of that water is going to evaporate. Some of that water is going to go into that gas form. So we need to take that away to find the gas by itself. So here is our scenario. Try to do this carefully so I don't get any water on my computer. All right, I've got a little beaker inside of here. If I pull it up just enough, you can see the water remains inside of the beaker. That's caused by water vapor pressure. The atmosphere is pushing down on the top of the water. As it pushes on the top, it's pushing the water up, like I have right here, and it holds up inside of there. We then put a tube inside of there, my great drawings there, I'm sorry, and which begin to collect gas. Now, the only way to make that water push out is when the pressure inside of there is equal to the atmospheric pressure, at which time the volume of liquid is decreased and being pushed out. So When we do that, the barometric pressure is going to equal the total pressure inside of there. So we have the barometric pressure we have there, 775.9 millimeters, is equal to the gas we're collecting, carbon dioxide, and water. So how do we find water vapor pressure? Well, down here, I have a chart. It's called water vapor pressure. You might want to take a screenshot of this. I might include this with the sheet of worksheets and stuff like that. But we look at the values. If we go back to the problem, we see a temperature. Temperature is 26. We go to 26 degrees on here. 26 is 25.2 millimeters of mercury. So all I have to do is plug that in. Now it's a simple case of subtraction. Using the calculator or just using your brain, if I take 755.9 minus 25.2, I get a pressure of carbon dioxide of 730.7 millimeters of mercury. All right, so that's Dalton's law. Graham's law deals with a constant called diffusion. Diffusion, the process going to an area of high concentration to low concentration. For here I have food coloring, high concentration. Here I have water, no food coloring, basically absolute zero concentration. If I take and put 1 drop of food coloring, you see it begins to spread out. That process of sending out through that is diffusion. And eventually, I don't want to splash it around too much, it will fill the entire thing. Now the concentration here is still going to be less than it was here, but it spreads out evenly through the process known as diffusion. Now, the actual gas law is expressed as a simple equation. That equation is R1 over R2 is equal to the inverse square root of the densities. So they take the second density, put it on top, first density, put it on the bottom, divide them, take the square root. Let's take a look at the problem. Determine the rate of diffusion of a gas with a density of 1.244 grams per liter as opposed to a gas with a density of 2.003 grams per liter. So we want to take the ratio of these two gases, 1 to 2. So we'll put the second gas on top, 2.003 grams per liter. First gas on the bottom, 1.244 grams per liter. Take our calculator, divide them. Now some of these are a little different. Some of the older calculators just hit square root. My calculator, you have to hit second function square root and then put that answer in afterwards. When I do, I get 1.269. Now that doesn't tell me anything. So we need to understand the ratio. If my ratio is greater than 1, then the first gas is moving faster than the second gas. If R1 over R2 is less than 1, then it's moving slower. So if we look here, we see that 1.269 is greater than 1. So we're going to say that gas 1, if they have a statement here, gas 1 is 1.269 times faster than gas 2. That's my answer. All right, I said there's 2 ways to do it. The second way I can do it goes like this. Now, wait a minute, Dan, Pastor Dan, there's no densities. How are we going to do this? Well, if we're looking at densities, remember densities are expressed as grams per liter. Is there a value that we talked about that involving volume and moles? Hopefully remember molar volume. Molar volume is 22.4 liters per mole. If I use that, my liters cross out, my 22.4 left, I'm going with grams per mole. Grams per mole is molecular weight. So if I take the inverse square root of the molecular weights, it's also equal to the rate of diffusion as a ratio. So in this case, we're comparing the molecular weight of oxygen, oxygen 16 on the periodic chart, times 2, 32 grams per mole. Fluorine is 38 grams per mole, 19 times 2. Now remember, this would be a life and death situation if I release these two gases. If oxygen gets to you first, take a whiff and you run, you might live. Fluorine, remember we talked about before, fluorine's extremely toxic. It will kill you. Go to the hospital. Don't go to the hospital, go to the morgue, you're dead. So if you get a quick whiff and run, are you going to live or die? Let's see here. So we're going to take oxygen over fluorine. So therefore, that means fluorine has to go on top. So it's going to be 38 grams per mole over 32 grams per mole. That number, if you take the calculator, 38 divided by 32, hit equal square root, however the calculator works, and I get an answer. I get 1.09. Ooh, that's really close. That's almost 1. They're almost dead even, but not by much. So that's saying there's no sig figs here. Let's make sure we understand it. Just for my class, when we do this, keep it at 4 sig figs. Oxygen is 1.090 times faster than fluorine. All right, there's two problems. Work those through, pause the video, give them a shot, refer back. We're going to see what we do. So pause it. Let's see what we get. Ready? Here we go for the first one. We're going to take our ratio. The total volume is 50.00 liters. So for just oxygen, 309.0 millibars. For the second one, it's densities. So therefore, we're going to take 3.0055 grams per liter over 1.0899. That's 5 sig figs and 5 sig figs. 5 sig figs. Carbon dioxide is 1.6606 times faster than the gas 2. We don't know what that is. Just say gas 2. All right, that's it for today. Take care. God bless. Have a great day.